So, the topic I will be discussing today is the Minibang in the laboratory. So, before going into the details, there are at least two terms here which I have highlighted. One is mini and other is a bang. What does the mean? Why one need to think the word mini? And there could be some other, other word as well. Little can be big, very big, or something like that. And to understand this, what you have to look into. This is how our universe has started. If you try to have a look at that picture, then probably it will be clear why this word mini is important here, and why when the word bang comes, it's something. It has something to do with a kind of blast. But what kind of blast? Does it mean a normal boom blast or something else? We will try to have a look into it. So, if you have So to start, when you have that sentence Minibang in the laboratory, at least you have some questions in your mind. That these are the questions mainly came into our mind when we start to think about the Minibang in our laboratory. What are they? When it all started. It all means everything, starting from mass, energy, our existence, something else's existence, and all others. And then, as you know that the whole system we are staying, this is the universe. And if you take that this is the universe, what are the constituents of the universe? When did it started? And then if it has started, where from it started, and then what are the constituents in it? And then there are something that if these constituents are there within the universe, there must be something to tie them. Otherwise, they will have a tendency to go apart or collapse. But so they are staying. It means there must be something which is taking care the form which is existing today. And then where do we all come from? We will have try to have a look into it, and then this basic constituents of the universe. By basic, it means when you have a matter at your hand, probably you will ask a question to yourself that does this matter a fundamental one? Then what we will try to do? You will try to break it up. If you can break it, then you will find that no, it's not the fundamental one. One can break it. So then what you will do? You will start going on breaking it into small pieces. The point where you can't break it further, then you will say that okay, now I have achieved a point where the pieces are fundamental. I cannot break it further, right? And this fundamental thing or elementary concept, it completely I should say it's not absolute. Why? Say if you look back in say around 1911 or 1910, 1920, then the fundamental particles people used to think of their nucleus and then proton, neutron, these things. 30 years, after 30 years, then people started thinking about no, these are not the fundamental particles. There are, one can break it up more and more, and those leads to the discovery of the quarks, which are the more fundamental one, right? Then what was the thing that restrict you to take proton, neutron, nuclear? Those are the fundamental around 1910, 1920. Probe, your way of looking. If you have only eye, nothing else, then probably the matter, smallest matter what you can see with your naked eye is the fundamental one. But you have some other, very finest eye, like microscope, then you will say no, this is not a tiniest one. I can see there are structure inside it. So this is the way of looking which will make you to take the fact that level of elementary or fundamental level of fundamental particles which you will take as the elementary one. Okay. Then let's if you try to answer these questions, you have to look the evolution history which are shown here very beautifully. So this is one of the model that probably at the very beginning 14 billion years ago there is a very high energetic blast which was the Big Bang, which is known as the Big Bang. And why it is big? Things associated with it, everything was big except its dimension. What was its dimension? It's a point, singularity. So it's a point like thing, and at a particular point huge amount of energy, this infinite amount of energy was concentrated. And you know, when you heat a water, first what it do? It start increasing its temperature, right? So when the energy of a system is pretty high, then temperature should be infinite. Temperature should also be very high. So at the Big Bang, at the point where this big blast happens, both this energy density, remember this is the energy density. So whatever, even if I forget to say that it's energy density and I'm misnomerly telling it energy, but keep in mind whatever I'm talking about, it's energy density, not the energy. Okay. So the energy concentrated at this particular point is infinite, and then it's blast. Just after the blast, it start. The first is what was the inflation, and this particular. This is the axis along the time. So during this course of time, see the time interval is 10 to the minus 36 second. During this time, nobody knows what was happening. Just it's inflate. And most of the things people used to talk about, those are speculative. But after this point, then we have model dependent calculations, phenomenological predictions or theoretical prediction in some sense, which will tell about that what was there. For example, after the Big Bang, this is the 10 to the minus 6 second to 10 to the minus 10 second to 10 to the minus 6 seconds. At this stage, matter started forming. At the beginning, no matter, only energy. I was saying it's energy density purposefully. So no matter, only energy. Then after a particular time, matter started forming. And don't know that how these, what kind of matters. And if you want to look into the matter, what kind of matter are there, you have to, either you have to go back in time 14 billion years ago, or you have to create this kind of blast in your laboratory. But be careful, this is a Big Bang. Energy is infinite, temperature is infinite. Can you do it in the laboratory? No. So we have a constant on energy density and temperature. And the amount of constant itself tells you what should be the word sitting instead of big. Either it's a little or mini or maybe micro, right? Then, another important part of this evolution, this is the evolution, picture of the evolution of the universe. So at the beginning it was energy only, and then it started forming some matter, some form of matter, and then these matters started finding their partners to form a more known matter to us, which is called like proton, neutron and all these things. So up to this, there is no as such matter which is known to us, which is detectable up to this. So up to 10 to the minus 6 second, where the energy scale, look at the energy scale, energy is of the order of GeV, 10 to the 100 GeV or of the order of TeV. The energy scale involved here is TeV, 10 to the minus 12 EV. And do you understand what this EV means? Electron volt. It means what does this electron volt means? When you throw an electron through a 1 volt voltage difference, it will gain some energy, and this is the amount of energy it indicates. Okay, and after that it starts forming some particles which are detectable, and these particles still, further they combine with each other and form a nucleus kind of thing which is visible to us, nucleus and atoms and molecules which are visible to us. And afterwards, more bigger and bigger structures forms, and this is the present universe we have. So what is the time scale? This is the about 14 billion years. Remember, this is 14 billion years. And what is the starting point? Big Bang. Do you know anything about before Big Bang? What was there before Big Bang? No. Just what we the start of the time, what we take as the start of the time, this is the time when this Big Bang happens. Okay. And then to summarize, what is the Big Bang? It is the point where a big burst happens with infinite energy density and temperature. It's clear? And then followed by an evolution. Evolution in a sense that first it was energy and then started converting into matter, and those matter combine among themselves to form visible world and this macro world of today's universe. And as I was saying, that it is considered as the starting point of our universe. If you want to know this evolution history, the photographs shown here, if you want to know this evolution history, there are two ways. One way is, as I was saying, you have to go back, you have to have some kind of time machine which can travel 14 billion years back, and which can still exist at the temperature we were seeing, or energy density. Then probably you know the history of the universe. But there are some indirect other ways around. So you can search for some candidates which might have created during Big Bang and they are still existing. And one such example is the cosmic microwave background. You probably heard of it, right? And in coming days you will find a more detailed discussions about this cosmic microwave background. So this is, in any kind of experiment there are two ways. Some systems used to emit some kind of information, and if we are intelligent enough, we can catch those informations and get the details of the system. Or a system is lying there, you are throwing something at it and try to look after it is interacting with the system, how it look like, and looking at the change you can have some idea about the information of the system itself, right? So this is, one is non-destructive, this one. Another is sort of you are probing, disturbing. So let's go back to our discussion. So one is to find a candidate which produced during Big Bang and still exist, and it has already detected, and you know this discovery, right? Okay. And then other way, try to recreate this bang in the laboratory, not the big bang in the laboratory, and let it evolve, and then try to have a close watch on it. And believe me that this kind of effort we have many, and it started from the Rutherford Experiment, which is very well known experiment. Do you know about this Rutherford Experiment? Yes, this was the experiment which told you about the structure of atom. Okay, so this is a sort of effort, you can say, which is giving you the opportunity to look back at the evolution history, not right at the point of Big Bang, but little later, maybe somewhere here. Okay. Then we have more sophisticated experiment than the Rutherford experiment these days, and the latest one is the Large Hadron Collider at CERN, and it has the capability to reach little more close to it, which is about 10 to the minus 6 seconds. I can say that it can reach up to 10 to the minus 6 seconds, but there is no reason you should believe me. You should believe in a way that there must be some experimental evidence which tells you, yes, something might have been created there, which corresponds to a time in the evolution of the universe which is about a microsecond old, right? We will try to have a look at it. Then you want to know the evolution history. There are two ways. One is non-destructive, one we want to create it. But this mimicking Big Bang in the laboratory, not possible, because of you don't have infinite energy or temperature. Pretty simple. But you can dim to create a bang in the laboratory still, but in small scale, where the energy involved is of the order of MeV to TeV, and it's of course a try to reach close to the origin of the universe, not exactly to the origin of the universe. What it called is a little or mini bang. So the word mini corresponds to the fact that during the bang, the energy density or the temperature is not infinite. It is finite because of our limitation. Okay, and this in fact is the topic of today's discussions for this session. We are talking about little bang or mini bang. How it look like? So assume like the Big Bang, something happened, a blast, very mini blast happened, and after the bang, like the evolution of the universe, it is also passing through same kind of stages. But here, first some stages which is a sort of plasma state, and then started forming detectable particles like neutron, protons or other particles, and then they combine to form this visible matter probably. And then once these particles formed, you have, since you are doing in the laboratory, you can have some kind of arrangements which can detect these particles, right? So you are detecting these particles which are coming from the little bang. So you are detecting, try to think in opposite directions. You are detecting, yeah. So and then you are tracing it back. So ultimately you are detecting the type of particles, its energy, its identity, its momentum, all these things by your detector, and you are trying to find where from it came, and you will find, yes, it's a little bang or mini bang kind of thing. But please be careful, there is a difference between little bang and the mini bang. First one is the time scale. See, if you take this time at which this little bang happens as the 0, the time when you detect these particles, it is of the order of 1 second. So this time span is 1 second compared to the time span where your Big Bang happens. This is about 14 billion years. So probably, we are placing our detectors right at here, okay, in the mini bang or little bang. You don't have to go to today's universe, okay. And other important thing is, in the Big Bang you don't know what was there before Big Bang, but in case of little bang, since you are creating it by some means, either by imparting energy to a particular point, and you can impart by this energy by colliding something. Usually people used to collide a beam, and this is one beam, this is another beam. So you let these two high energy beam to collide at a particular point, let all their energy be imparted at a particular point in such a manner that the energy density matches the criteria to create a bang like Big Bang, but with very reduced scale. Okay, understand? I mean, am I communicable, or is there any difficulties what I am saying? I mean, what I am trying to communicate it? Everybody is understanding or not? I mean, there is no point if I mean, go on saying and you don't understand. Okay. Then, if you see, if you look at this figure, if you want to understand the whole thing, you need to understand the whole thing. Otherwise, you cannot have, I mean, information or I mean, sort of understanding about the evolution unless you know the whole picture. And I have divided this picture into 3 portions. One is preparing for the bang. So you have to create the bang. You have to make this energy concentrated to a particular point. For this, you need to have a preparation for it. And then, I mean, just after the bang, there might have a lot of things happening inside. So just if you look at this, just after the bang, there is a system. First it was the energy, and then it is, I mean, transforming into matter. So there are some processes going on there. So you have to understand those processes, so that when you detect them, you apply those processes back and you reach this point of Big Bang. Okay, but I mean, unfortunately, you don't know exactly what are the processes and when they are occurring, which processes is occurring when, and all these things. There are a lot of processes, but you don't know their sequence, whether they are sequentially occurring or they are parallelly occurring, and all these things. But there are some ways, and if you let the little bang to be happen million times. So we have 1 million little bang, and 1 million time same thing happening. But the processes happening there, lot of processes happening there, they are not following exactly same sequences. But now what you have, because of 1 million little bang, you have a statistical description. For you, by statistical means, when you don't have, say, pick a particular student. If you don't have the information of a particular student, then what we used to do, try to put the student to the school he or she belongs to. And then what I will study, I will go back and try to study what are the usual common natures of the students for those schools, for that particular school. And at least I have few information about a particular student. So this is sort of getting information we don't have detail about the system. So sort of averaging, getting the information by means of averaging. Okay, and there exist many theoretical and phenomenological models as well. You can try to match them and tune them so that their interpretation can be acceptable and reasonable. And once this evolutions is completed, then what are there? Particles are coming out, and those are detected, and this detection itself is a huge task. And this is the one of the major part we used to do in our laboratory. And we spent very big amount of time of our effort for detection of this kind of particles, signals. Not only, you can detect these particles. It's not a very big job. Why? I will tell you later. After this detection of these particles, you need to have, you need to extract the information of your interest. There are a lot of informations these particles are carrying. But you don't need all those informations. You need a particular information which is useful to you. So you have to extract those informations as well. So these itself are techniques, and they are called data analysis techniques. And believe me, this is a huge task these days for this field, of course. So we try to have a look for all 3 parts of this picture. Then, before going to this, these are very simple things for those who belongs to universities or colleges, but for school students probably it will be interesting. Before going to these big things, let us understand some basics and necessities as a tool for our understanding. First of all is the interaction and the universe. Interactions ruling the universe. Excuse me, this pointer is not working. So, oh, now it's working. So, these interactions ruling the universe. What is the general idea for the interaction? One thing, when two particles is touching each other, you know that what does it mean. But even if they are not touching each other and they are feeling existence of other, you have to have some kind of interpretations how it is happening. And this is the present day understanding that two particles, this is one particle and this is another particles. When it is, it is feeling its existence by means of exchanging something. So it's like it is kicking a football and the football is hitting this person, and it means when he is kicking, he is feeling a backward force, right? And when the ball is hitting him, he is also feeling a force. And if you know why this football is hitting him, then you know that yes, somebody is sitting there and kicking this football. That's why this football came to me and hit me, right? So the general idea for the interaction is when there are two particles, they exchange something, probably not visible to you, but they exchange something. This is, and because of exchange of this particle, they experience one another's existence. This is the very simplest explanation for the interaction. Okay. And these exchange particles, they are boson after the name of Bose. And but these boson, this particle, exchange particle, can be different depending on the type of interaction you are talking about. And you know that there is not a single interactions exist in the nature. There are four kind of interaction. So try to look at those four kind of interaction. Let us first try to look at the one which we know are familiar most. This is the gravitational force, which is responsible to make the apple fall on the earth. This is responsible for a particular planet to move around a star. So, this is the force which we familiar most and exists all over the universe. It acts on what? It acts on any particle have mass or energy. For you, this mass and energy, they don't have much difference when you are talking about very high energy scale. We will be coming to that. Just take this, assume that mass and energy, they are behaving in the same manner, not exactly same manner, be careful, but as far as this interaction is concerned, just assume this mass and energy, they are behaving in same manner. And how this gravitational force behave, as you go away from each other, this amount of force is decreasing. And this dependence itself told you that, tells you that this is an infinite kind of force. Even if you go infinite distance, you still feel very little but non-zero gravitational force. It means like this only, right? So gravitational force has infinite range, remember this. And then is the electromagnetic force, and this is responsible for the visible matters. This is responsible which keep the visible matter intact. It is holding the visible matter. So proton, electron, they are they got attracted and sitting in a combination because of this electromagnetic force. And it is also behaving like the gravitational force 1 by r square, but the strength of the electromagnetic force is roughly about 10 to the 36 times stronger. So, if you keep two particles at a particular distance and you calculate the gravitational force and the electromagnetic force acting between them, you will find the electromagnetic force is much more stronger. Okay. And it acts when there is existence of electrical charge. It can be positive or negative negative, any combination. And then comes a weak force, weak interactions. This is responsible for subnucleonic domain, where for example when a neutron breaks into a proton, electron and antineutrino. This process is called, do you know what this process is called? This is called beta decay. Okay. Are you familiar with beta decay? Have you heard about this radioactive things, radiation? So, this is a sort of radiation. Beta is a kind of radioactive ray. Okay. It is coming out from the nucleus, and how it comes? When a neutron converted into a proton, then it gives an electron, very high energy electrons. These electrons is coming out as a not discontinuously, rather continuously, and this is a beta ray. This is called a beta ray. Okay. And the force involved here is the interaction involved here is the weak interaction. Okay. And I forgot to mention this, that if you look here the exchange particle is called graviton. This is not yet discovered. There is a reason behind it. The energy scale associated need to discover this graviton yet to be reached. This is not yet there. But for electromagnetic force, the exchange particle is photon, it's a light. I'm telling it's a particle. So photon is light and it's a wave, you know that, right? But when the energy of the light is pretty high, you can consider it as a particle as well. Particle nature is dominating there. Okay. And then in case of
here all the three
yes,
particles
yes,
they are different.
They are different. Okay. So here in case of weak interactions, unlike the other two, there are three three particles which can be exchanged among them depending on their nature of the interactions. When a charge is involved, then exchange particle should be W plus or W minus. When it's not a charge but weak interaction is happening, then also then the exchange particle will be Z0. Okay. And unlike the other two cases, not other two, the electromagnetic cases where photon was there is no mass for the photons, Here they have quite large mass. Okay.
Which one is the heaviest out of these three?
Among this Z. And then the strong interaction. For the strong interaction, it acts among, what does the strong interactions came into the picture? Inside the nucleus, right? The way proton and neutron talk to each other is a strong interaction. And the constituents of proton and neutrons, they talk to each other. The way they talk to each other is also a strong interactions. And the constituents of neutron and protons, they are quarks and gluons. Okay. And quarks and gluons talk to each other by exchanging a particle boson, which is the gluons. And remember, unlike the photon case, here gluons can be many. At least type of gluons involved here is 8. 8 are involved. Okay. And the force is, look at the force. Here the force is, this is the expression for the potential. This weak interaction and the strong interactions, they don't have infinite range. They have finite range. So after a certain distance, they don't, you cannot feel them. And this forms itself tells you that. If you, if you look at this form, so there is a dependence 1 by r, it will make it infinite range, but there is another term e to the minus. So, this tells you exponentially decrease. So, one is increasing it, one is decreasing it, exponential is decreasing it, another one is, no, this exponential fall is much faster. So, after a certain distance, this will be dominating this exponential decrease and make it, finite. And same thing like in case of strong interactions. And the questions I was talking about at the beginning, why this strong force is finite in nature. The reason is these gluons. See, you know the photons, they don't have any charge. Have you ever find instances where a photon is going this way, another photon is going this way, and they are interacting, talking to each other? No, they never, right? But gluons do. The big difference is gluons have charges, and these charges are not electrical charges, they have different type of charges. Those are called colored charges. So, for the time being, you guys take this fact, you guys take this fact that like electrical charges, there is one other type of charges which is called colored charges, and strong interactions act among these colored charges. When there are two colored charges, these strong interactions happens. And for the time being, you just take this fact that this this formula and all these explanations are something similar like this electromagnetic case, except a difference. The difference is, here quark and gluons, in case of electromagnetic interaction, you can have a free electron, you can have a free proton, right? But in case of strong interactions, this quark and gluons, these color charges, these are these are color charged particles, they are not freely available. Okay, they are confined, they are always confined. You never find in nature a free quark or free gluon. Okay, these quark and gluons always combine among themselves in a favorable manner to form a object for whose the color is 0. That's why you never find these colors. If you don't have color, then no strong interaction, right? Okay, and this is the strongest force. It's roughly 10 to the 38 times stronger. And this is the force we will be discussing today for this session mostly. So, this is the force which is responsible for the interaction among quark and gluons and formation of composite particles like protons, neutrons, and all other particles. And if you like, this is a sort of a table summarizing and comparing these relative properties of these 4 kind of forces, where they act, what are the exchange particles involved, and what are their masses, relative strength, and the range. Okay, then once you know the type of interactions, then try to have a look that what are the fundamental building blocks of the matter. First, this is the matter, what you can see with your naked eyes, and its dimension may be of the order of 1 meter. Then if you start breaking it, you will come to a point where you will find a molecule where it has lot of atoms sitting inside, right? And its dimension is about of the order of angstrom, 10 to the minus 10 meter, right? Still, you can have a very good microscope and you can find the molecular structure. If you point your microscope to the matter, you will find the structure inside it, right? But if you still break these atoms, try to see what is inside atom, then you don't have any such kind of simple microscope to find it. You have to have some kind of experiments. The first one is the Rutherford experiment. This is the Rutherford experiment. Okay, so these Rutherford experiments actually what it did, it is basically a microscope to see the structure of the atom. Is it acceptable to you? So it's experiment, don't say it's experiment, it's a microscope to see the structure, more finer structure like atomic structure. Is it okay for you? Okay. Now, if you modify the Rutherford experiment little bit and increase the energy of the beam you are throwing, increase the beam of the alpha particle you are throwing to the gold foil, then probably you will see much more deeper, which is the experiment, much more deeper. This is the structure of the nucleus. It comprised of neutron and proton. And you know when this how this neutron discovered, this was the Chadwick experiment, right? This is, you can take, this is one shot of Rutherford experiment, modified Rutherford scattering experiment. And even if you still want to go deeper, then the structure of the proton or neutron, you have to modify more and more this Rutherford experiment. You have to increase the energy of this incident alpha particle more and more, maybe of the order of huge, 10 to the 12 eV, 10 to the 12 electron volt, where for Rutherford experiment it was only 10 to the 6 electron volt. Here, to look at the structure of the neutron and proton, you have to have the microscope where the energy scale involved is 10 to the 12 electron volt. And where from this 10 to the 12 electron volt come into the picture? Try to have a look. And it is pretty much important or very interesting that after a certain point there is no as such simple scope which can let you find the inside structure. There are only sort of, either simplified or sophisticated and modified scattering experiments which act as microscope for you to find the more finer details. Yeah.
What is
For the time being you can take these partons as the constituents of the neutron and proton and the most fundamental one. So parton is the generic name for quark and gluons. Okay. As I was saying, so after a certain point you have to have only scattering experiment with more and more energetic beam. And then what we have, if you have this kind of scattering experiments in your hand, you have at least few fundamental particles, from the present day's experience, few quark and gluons.
What's the difference between quark and gluon?
Quark has mass, but gluon don't have. Yeah.
It's a carrier.
It's a carrier. It's a carrier. But these carriers are very much special in a sense that it can also interact among themselves. Yeah. Okay. And so for particles there are 6 type of quarks, and when you have particle you always have antiparticle for it. So you have 6 type of quarks, 6 generation of quarks, and they are antiquarks. So 12 quarks, and then leptons. This electron is a fundamental particle. You cannot break, as of present understanding, you cannot break electron into pieces. And like electron, there are 2 more particles like electron. One is muon and another is tauon. And when you have a particle like here, when you have a particle, it has a close associate. I have arranged it something like this: up quark and down quark, they are associates. So something like this, you have also have for electron a corresponding neutrino. It's also a particle, its mass is close to 0. And for muon it's a muon neutrino, and for tauon it's a tauon neutrino. So here 6 particles, and there are some force carrier which are photons. For this, gamma is photon for electromagnetic force, Z0 and W plus minus for weak interactions, and G is for strong interactions. Important note, unlike electron, quark do not exist freely. They always find a favorable pair and form a colorless one. Okay. And then 2 very important tools. One is the Bogie hypothesis. What does it say? If you have a particle of momentum p, it has a wave nature, and it can be calculated from this. So, a particle can have both the nature, but when you toss a coin, you find a particular face is, I mean, you can see a particular face, right. Something like, I mean, in something like this, in case of this the Bogie hypothesis, wave particle duality, for a particular type of interaction or understanding, a particular nature is always dominating. For example, when you are seeing diffraction or this diffraction kind of experiment for particles, it is not the particle nature, rather the wave nature. But when you have a reflection or refraction, they can be understood through particle nature. Okay. And then, so what it tells, I mean, one very important thing is, see, if you have a particular particle with momentum p, you calculate the corresponding. Okay. Now, just think of a situation, you have a particle here, you want to, I mean, you want to measure this particle. So, one way is through a light, what you see, and let the light come back to you, and you see the light coming back and try to find the light you have thrown and the light coming back, what are the differences, and you will find what is the size of the particle acting like a reflector, right. For, I mean, this very thumb rule is, whatever you are throwing to a particular particle, the dimension of this wave should be of the order of the dimension of the particle you want to measure. So, take this thumb rule as, I mean, a very important one. When there is a matter, you want to probe it, the wave with which you want to probe, its wavelength should be of the order of the dimension of the matter itself. Okay. Now, if you want to look at the atomic structure, what is the dimension of the atom? Dimension of the atom is the angstrom. So, put 1 angstrom, put the value for the Planck constant, try to find what should be the momentum of the particle you have to throw. Okay. If you want to see the structure inside a nucleus, what is the size of the nucleus? About a Fermi. Say about a Fermi. Put the value Fermi, I mean 1 Fermi here, try to calculate what should be the energy. So, with the LHC 7 TeV energy, you can reach, I mean, the corresponding length scale is 10 to the minus 18 meter, 10 to the minus 3 Fermi, 10 to the minus 18 meter. Okay. So, with the present day available energy, at least you can probe is the 10 to the minus 18 meter, and people are, I mean, people are saying that this is the dimension of the quark and the electron. So, the dimension of the quark and gluons is 10 to the minus 18 meter. So, 1 by 1, then 18 0, this small. Okay. Now, who knows, if in future, near future, if you have, instead of TeV energy, if you have 1000 TeV energy or 1 lakh TeV energy, then the length scale will be 10 to the minus 25 or something like this. Then probably you will start saying that no, quarks still have some structure, right. So, it's sort of availability which tells you that this is the fundamental particles. Okay. And then one more important is the Einstein, this mass energy relationship. So, this energy and mass, they are, I mean, one can convert this energy into mass or mass into energy. And at this point, this Big Bang, just after Big Bang, it was started with the energy, and then it converted into mass. So, there is a interpretation for it. I mean, one can do it, and this is the Einstein's mass. This is coming from the Einstein's mass energy relationship. So, these together, what it tells, if somebody throws a ball, it can behave like a ball itself, or one can interpret it as a, instead of a ball, it is like a wave. Okay. And in either of the cases, for either of the cases, we can calculate the energy for it. This is the form of energy and this is the form of matter. And for this energy, if you have the energy and you know with this energy what is the mass of the particle one can create. So, we have the energy wave, apply the Bogie hypothesis, calculate the calculate the energy, and for this energy try to calculate the mass. Okay. Then now till now what we have tried to make the very basic understanding to go through the details of this topic. So now let's go to the topic where we have to create the band. How can we create the band? As I was saying, this is the earliest one, Rutherford scattering experiment, where a alpha source was there. These alpha particles, which is of the energy of about MeV, they are interacting with a gold foil, and it is giving something which give you a information about the atomic structure. So with the Rutherford experiment, you are going back right at here, where these atoms are existing around here. Okay, the energy scale is MeV. So it is not pretty much close to the Big Bang. Okay, and then how can you collide this two particles? There are two ways. One way, a archer is throwing a arrow to a target, fixed target. So a target is sitting and you are throwing something. You are throwing and hitting a particular energy of the this arrow is just imparted to a particular point here, and this energy is available for new particle creation or new physics. And other way is, two archer, they are pointing each other and let their arrow meets at a particular point, and this is called a collider type of experiment. You can understand what is the difficulties. This is the real life difficulties. When you have a single one, bowman, he is targeting a particular point, you know how difficult it is, how many times you have to practice. But think of a situation, a man is throwing an arrow, and looking at the arrow, you have to target that arrow, tip of the arrow, so that it cannot hit you. You have to crash it at the middle of the flight. Okay? So you can understand how much difficult it is. Now think of a situation, it's a arrow. Instead of arrow, if you start decreasing the thickness, not the thickness, width of this arrow, smaller, it's like here, even less. If it is like that, dimension of 10 to the minus 15 meter, think of the situation, how difficult it will be. Collider type of experiment, earlier days this collider type of experiment was not there. After the development of the techniques, people started getting expertise in developing such kind of state of the art technologies to find this kind of collider experiment. And it has huge advantage in a sense. When you throw you are throwing something, whole energy will not going to be imparted to a particular point. Why? Because of momentum conservation, right? So when you are throwing something, it is hitting. To conserve the momentum, some energy will be taken away by the target itself, and some energy will be available for your study. But when you are hitting this, same energy coming from opposite directions, same velocity coming from opposite directions, the total momentum is 0. So to conserve momentum, you need not to spend any energy. So whatever energy is there to the beam, the whole amount will be available for your purpose, production of new particles and everything. And this is actually people used to do at the Large Hadron Collider itself. So this is the two rings, 27-kilometer ring at CERN, Large Hadron Collider, and there are 4 intersecting points. See, so 2 beam lines, they are intersecting at a particular point. You have to have precision in such a manner that 2 photons collide at that point only, not other points. And these beam lines are something like this. You have to, if you increase this, pop up this position, then it will be something like this. So 2 beams, they are meeting at a particular point, not meeting, colliding, and dumping their energies, completely, and this energy is in the form of this stage, and then it is starting converting into matter. Okay, and this Large Hadron Collider is designed for the energy 70 eV, and then we have created a bang, right? You have created a bang. Then what happened just after the bang? Just after the bang, in case of big one, there was a inflation, and after that this energy started converting into matter. Here, since we are not reaching the same amount of the energy density, probably you will reach a region somewhere here where it is not completely a energy, rather mass is also there. There must be some quarks and gluons, more fundamental particles, and once they are there, they will start interacting among themselves, right? So quark and gluons must be there. Quark can interact among themselves, quark can interact with a gluon, or gluon also can interact. And another important quantity is also involved here. This is the photon. Photon is the candidate which can come from the very early stage, just after the bang. When quark and gluons are only there, then also these electromagnetic photons can come. So this photon is a very very important candidate, and there is one more reason behind it. Photons don't interact strongly. It don't interact strongly.
It's a colorless particle.
Yes. So quark and gluons, they have a color charge, not electric charge. These charges are called color charge. But quark and gluons, you cannot find freely. So they always combine them among favorable pairs, and they combine in such a manner so that the total color charge is 0, and for those particles it is called colorless particle.
Both quark and gluon have color.
Colors, yes. Excuse me. These photons, since they don't interact strongly, even if they are produced just after the bang, they will not interact. So a photon which is produced here, it will not going to interact with the quark and gluons and all these things, all these stages. It will remain uninteracted and come to your detector. The beautiful part of it is photons which is created just at the bang, it is not only traveling in time, it is also watching what is happening as the time passing. Understand what I mean? So photon carry the information. Once a photon is produced, say here, it is not interacting, but surrounding it, or quark and gluons, they are interacting, and this photons, it is watching this but not interacting it. So it carry the information without any disturbances. So photon is one of the very beautiful observable. If you measure very accurately, it can give the whole history of the universe, and that probably is the reason this microwave background is carrying this very important informations. And this is another picture. So just after the bang, it is a soup of partons, quark and gluons. This is more like in a state of plasma, and then as the time goes on, it will expand, right? So volume will increase, and as the volume will increase, why? It will spend its internal energy to expand it, right? And because of that, temperature will also decrease, and so the energy density. So just after the bang, you have only partons. These partons interacting among themselves strongly. So they are active both chemically and kinetically. After a certain time, partons, they found their favorable partner and combine in such a manner so that a colorless object formed, like proton, neutron, and all these things. And there is no such chemical reaction, no new particles, right? But still they can interact among themselves, like the way when you have a gas inside a container and the gas particles interact among themselves. Excuse me. And then after this, after some time, this kinetic type of interactions, it will not be there. So it will be settled against this kinetic and chemical interaction. So sort of equilibrium. And then since it is not interacting, it is ready to fly. It will be going out, and once it is in a state of going out, then you put your detector. It can be a fluorescence screen where a photon hit and a light is coming and you count it, or it can be a gas where a very energetic particle is passing through and ionize it, and then some charge is produced and collect the signal. Okay. And then you have to detect the signal. So think of a situation, one proton is colliding with another proton. Then depending on the energy of this colliding proton, the number of particles created is this many. Each line corresponds to one particle. At LHC energy, the number of particles is about 200 in proton-proton collisions. We used to think that proton is a fundamental particle, no? So at least it has 3 quarks, it also 3 quarks. So you can take different combination among them, right? So this many particles. Instead of proton, if you let lead collide on another lead at LHC energy of the order of TeV energy, then these many particles. Think of a situation, these many particles, but all these particles are not important to you. Probably for you only 10 or 12 particles will be important. So you have to find those 10 to 20 particles among all this junk and explain the actual physics processes or the information. Okay. This is the thing we want to do. And this, see, in case of PP, the size of the bang, the extent of the bang is little less compared to when a heavy ion is colliding with another heavy ion. So the size of the bang depends on the particles which are colliding. Not only that, their energy as well. And then what to detect? After the collision happens, there are a lot of particles are coming. It may be photons, it may be proton, it may be neutron, it may be pion, kaon, and blah blah blah. Many particles, many type of particles. Many type in a sense, they may have different masses, they may have different charges, they can interact differently. So depending on them, there are different kind of particles. So it can be both massive or massless. It can have a different, a wide range of velocity. So a particle has velocity 1 meter per second, can be detected by some detector. But if it is moving, say 1 kilometer per second, can you detect with the same detector? No, your detector should be different. So you have to have options for a wide range of detection technique to catch the whole picture in case of this kind of bang experiment. And it may have different charge states. So depending on the nature of the particle and their interaction, detection could be of different type. And this is the simplest, one of the simplest technique. See, this is a very small, say container. Inside it there is a gas. If you let one particle passing through it, it will heat one of the gas particle inside it. When it heat, it will ionize. So electron and ions. There is a wire inside this tube, and the wall itself is also a conductor. Give some voltage difference to this wire, central wire, with respect to the wall. Because of this voltage difference, whatever charge is produced, they will be attracted. And because of this attraction, a electrical signal will be induced, and that signal you can collect. So if particle is passing through, it is losing some energy, producing some charge. This charge is collected at the wire and it is producing a signal. So a signal means a particle is passing through the tube, right? This is the simplest one. And depending on the type of this particle you want to detect, this volume can be of different type. It can be gas, filled with gas or liquid or solid, or it can be a single detector, or it can be an array of detector, many detector. Say for example, you have 10 detectors coming at the same time. If you want to detect 10 particles at the same time, then you have to have a detector finely segmented, small spaces, so that a particular particle is hitting a particular detector, not all particles hitting a single detector. If all particles hitting a single detector means you will get a one information. Okay, you don't want to lose this information. Basically, whatever you want to do, whatever advancement you do, ultimately what you measure, what type of particle, the identity, whether it's a proton, it's a neutron, or it's a pion, or something else, its mass, its energy, momentum, what is the track, etc. And when you have a bang, what is the best way to place the detector? Best way would be like a sphere. So at a particular point, all these particles are coming out in all the direction, right? You don't want to lose a single particle. You want to detect each and every particle. So the easiest way would be to, arrange a detector so that it can cover the 4 pi, all the 4 pi. But you cannot do it. Why? You have to keep option for 2 beams coming to meet. You have to, since they are detectors, they have lot of wires, they have lot of arrangements. So you cannot keep a spherical like of thing. So what is the closest thing to the sphere? This is a cylindrical kind of thing. And as I was saying, there are different kind of particles. It cannot be a single detector. So what you do? There are many detectors. All are of cylindrical shape. Okay. So the innermost detector should be such which will sense low energy particle, and the high energy particle pass through it. Then you put some detectors which will sense intermediate energy particle, and at the end very high energy particle. Okay. And this is the actual experimental setup. This is the experiment which is Atlas at the Large Hadron Collider. There are 4 big experiments: ALICE, Atlas, CMS, and LHCb. This is the Atlas experiment. Actual experiment.
These different detectors have
different. Yes. So ALICE is devoted for this finding the evolution of this history. So arranging the detector, how to arrange? This is the very simple schematic. So something is coming, you have some arrangement to select. You don't want to select all the particles. You may have thousands of particles. You don't want to detect them. Your detector can sense only one type of thing. Then you select them. Then put a arrangement where a warning signal can be generated. This warning signal will be generated, and it is passing to the next step. So one particle is passing through it. It is creating a warning signal. This warning signal tells you that be ready, something is coming. Then this is a real detector. This is a real detector where a particle is hitting, and once this information is going there, then this person is noting it down. So important part is selection, warning signal, detection, and then recording. In actual experiment, this is one of the actual experiment. Some particles are coming. Say you want to detect only electrons. A Cherenkov kind of counter you can put it here to select, and then put a scintillator. This is a trigger scintillator, trigger detector. So it will trigger the next step. It will activate the next step. So it will be activated. Then you detect them, measure them, and then ultimately record them. So in present days it is not on the notebook, it is on the computer. Okay, so this was the bang, and this is the actual experiment look like. This is the ALICE experiment at CERN. So bang is here. Surrounding this there are many detectors. At least you can see 19 detectors are there. So in this experiment there are 19 detectors, and among them there is a detector called Photon Multiplicity detector, which was designed and developed in India. So this is the how this photon multiplicity detector look like. So this is your Large Hadron Collider beam line. So around this beam the detector is sitting there. So this is basically, I mean, there are 2 lakh detectors arranged in an array and put there. So photon multiplicity detector basically is 2 layers of detectors, each layer contains 1 lakh of detectors, small gas detectors. How it works? It works, I told you there are 2 layers of detectors. This is one layer, this is another layer, and in between them there is a very highly dense material. So when a photon is passing through one detector, since it is neutral, it will not going to ionize the gas, and then a very heavy material, in this material it will create few particles, and those particles will give heat in the next layer. So you will have many heats at the second layer. So no heat at the first layer, but many heat at the second layer, it is photon. But if you look at other charged particle, it will give a heat here, since it is a charged particle, but it will not going to produce any particle inside the dense matter. It will give again single heat at the second layer. So it is a charged particle, and electron will do same thing, but it will give, since it is a charged particle, it will give one more heat here. Okay. So by this what you detect? You detect photons. So this detector means to detect photons, light, okay, number of photons and their energy. What do these photons inform us? You measured photons, it's okay. Somebody may ask that what is the need of measuring these photons? By spending so much of money, so much of effort, so much of technology, what is the need? See, this is this x-axis is the this momentum. For you, for the simplicity, or 2 minutes. 2 minutes. Fine. So this is, you can take it as the energy, and this is the number of particles. Okay. So this is the way these photons are distributed, and there are calculations. These calculations are shown with these lines. So that this, what it tells, these photons are distributed exponentially, and the parameters associated to the exponential tells you about the temperature. Okay, and these are called direct photon. Direct photon means these photons came out at the very beginning, just after the bang. So if you calculate the temperature using these photons, which temperature it will give? Temperature just after the bang, and the temperature experimentally we have found it is like 5 trillion. 5 trillion temperature. This is the.
It will come through some detector and it will produce some.
No. These particles are not. This temperature is not coming. So photons, they are coming. Photons are coming from a bath. Say you have a bath, and from this bath some light are coming. If you find out the distribution of the photons there, and
it is surrounded by some detector.
Yes. This photon, not metal sheet. It's a photon multiplicity detector. You probably you are worried about the radiation. So yeah, radiation. To protect other things from the radiation, arrangement is there. Shielding, as proper shielding is there.
But how can you catch that photon directly?
No, since photons once produced, they are not interacting with the rest of the evolution, since it is electromagnetic and the system is strongly interacting. They are interacting through strong force, and photons, it is not interacting so strongly. Oh, so that is, once you have detected these photons, this is the detection of the photons. This is not the creation of the photons. So photons, those are coming, you are detecting. So from this technique, you are counting and finding the dense energy. What else? You can measure from this bang how many total particles are coming from the bang. It gives you what was the energy density just after the bang. How harder or softer it is? What is the momentum range of these particles? It will tells you what was the state when these particles was produced, whether it is in a state of hadrons or it is in a state of partons, or whether it behaves like a liquid or gas or something else. Identification of these particles, and are these particles coming out uniformly? Okay, and all have different importance. Now all together, these results indicates these systems after bang might be in a soupy state, plasma state, which consisted of quarks and gluons. And by this we can reach Big Bang, not exactly, a microsecond away. And you know, in this evolution, what is the weightage of this microsecond? So with this, at least you have gathered more and more knowledge, and we are rightly stepping forward to explore this bang, getting answers, if not answer, at least hints. Thanks a lot, the organizers of this Vigyan Samagam. So that's all. Now, if you have some queries or questions.
Cosmic background radiation, which information do you get from cosmic background?
Let's go back to the photon distribution curve.
Photon?
Distribution curve.
Oh yeah. Yes.
Yeah, so what does this represent? Like, what are the axes?
Axis?
Yeah, like, what are the quantities?
So x-axis is the momentum. X-axis is the momentum, and y-axis is the probability of creating these photons. So cross section of photon productions.
So the rate curve is the exponential fit, right?
Both are, if you look at this, so there are two calculations, two theoretical calculations. One is this exponential fit, which is red one, and other is direct photon calculation using perturbative QCD. It's like QED calculations you have done, field theory. So a field theory calculations, theoretical calculations, this theoretical calculation gives this curve, and this calculation gives you this curve, this exponential. And people used to take this, that photons at the very beginning they distributed exponentially, and that's why from this exponential fit, the parameter they have got 297, they put this as the value for the temperature.
So why is the curve not along the, why is the red line not along the curve?
Red line not along, okay.
Yeah, so
That's
it could have been
a good one. So as I was saying, photons can be created at the very beginning. It can also be created after say 10 to the minus 10 seconds. So photons can be created at different stages of the evolution. So photons coming from a particular stage, it will follow exponential fit with a particular parameter set. Photons coming from later stage, it will follow exponential fit, but not with the same parameters, different parameters. So it means all these photons, they are not coming from the same stage, though they are direct photons, but not from the same stage.
Anyone feel free to answer?
Please raise your hand whoever wants to answer this question.
Okay, so what is the age of the universe? Anyone? Okay.
Got the answer?
Yeah.
What is the value? 13.7? So everyone knows the exact answer.
Exactly. Okay, now tell some characteristics about the Big Bang and the Minibang and some difference. Anyone? One at a time, please.
Not audible, madam.
Sorry?
Not audible.
Okay, so I was asking for some characteristics of the Big Bang and the Minibang, or the difference between them.
Please raise your hand.
Yes, you.
Okay.
Big Bang can be.
1 minute, 1 minute.
Within the lab.
Wait.
Big Bang cannot be. She's on.
Minibang can be created within the laboratory, but Big Bang cannot.
Okay. And another one?
Okay.
Big Bang has high energy density, but Mini Bang has finite energy density.
Big Bang high?
High energy, infinite.
Anyone else? Another is
From boys?
we don't know what was there before Big Bang.
Okay, there
But
is
yeah.
one. So
Okay. One more.
In Big Bang the temperature is infinity, but in a mini bang the temperature is finite.
Yes. Thank you.
you have listened the talk very carefully. Good.
Okay. Okay, how after the little bang or mini bang, how did the system evolve?
You guys, so for your university students, how this minibang, from minibang to the state where these particles can be taken, how they have evolved.
How they have evolved?
Initially, what was there? Worked on plasma issues, and then it was chemically reacting to themselves, chemically and both, kinetically. After that, chemically it stopped, only kinetically, and then it got a state where it is equilibrated against chemical and kinetic. And then after that, colorless particles form, they are equilibrated, they are ready to fly and detected.
Okay. Then going to the detectors, about detecting particles. So, here was one detector, the PMD. So, how does that detect photons? How does PMD, the detector PMD, that detect photons? Or any detector, how will it detect photon? Okay, how does photons interact with matter? Electromagnetic interactions, and there are three types: scattering, Compton scattering, yes, photoelectric effect, yes, and another one, pair production, yes. Okay, so the time is up, and anyone has any queries or anything, so you can ask me after some time, or you can ask sir after some time, after the session is over.